Hi guys, myself Jaber bin Umar from EC department. Today I am going to explain about working of R-2R ladder type in digital to analog conversion. Digital to analog converters are the circuit which converts digital signal into analog electrical quantities related to the digital encoded input number. The digital to analog converter are also used in many other applications such as cathode ray tube display system. The DAC can perform its conversion in either serial or parallel form depending upon the application in which it is used. Example: process control applications. Now DAC accepts n-bit digital input words say B1, B2, B3, so on Bn in binary format and produce an analog output signals voltage out proportional to input digital signal binary input. Binary input is defined as a basic block diagram of commercial digital analog conversion is shown in the figure, and this figure is generally divided into 5 parts: input gates, n-bit register, voltage switch, resistive swimming network, and amplifier with a reference voltage source. Binary B1, B2, B3 is transferred to the input gates, then again it is transferred to the n-bit register. DAC techniques. There are mainly two techniques used for digital analog conversions. The first one is binary weighted resistor digital analog conversion, and the second one is R/2R ladder digital analog conversion, in which only the binary weighted resistor digital analog conversion is to be discussed. Before we move ahead, let me explain you binary weighted resistor digital analog circuit conversion. The binary weighted resistor digital analog conversion uses an operational amplifier to sum n binary number weighted current derived from a reference voltage resistance via current scaling resistor. Example: 2R, 4R, 8R, so on, as shown in a figure. Switch positions are controlled by the digital inputs. When digital input is logic 1, it connects the corresponding resistance to the reference voltage VR, otherwise it leaves the resistor open. For on switch, I equals to VR by R, and for off switch, I equals to 0. Here, operational amplifier is used as summing amplifier. Due to high input impedance of amplifier summing, current will flow through RF. Hence, the total current flow RF can be given as IT equals to I1 plus I2 plus I3 plus so on IN. The output voltage is the voltage across RF, and it is given as VO equals to minus IT RF. Where V0 equals to minus I1 plus I2 plus I3 plus so on plus IN RF equals to minus, where I1 equals to A1 VR by 2R I2 equals to A2 VR by 4R plus I3 equals to A3 VR by 8R, so on. In equals to AN VR to NR RF. V0 equals to minus VR RF. A12 minus plus A2 minus 2, A3 2 power minus 3 plus so on an 2 to the power of minus n. So this equation shows that the analog output voltage is proportional to the input digital world, where RF equals to V0 RV0. V0 equals to minus VR A1 2 to the power of minus 1 plus A2 2 to the power of minus 2 plus A3 2 to the power of minus 3, so on, plus AN 2 to the power of minus n. Now we are going to discuss about R-2R ladder. An enhancement of the binary weighted resistor DAC is a R-2R ladder network. This type of DAC utilizes Thevenin's theorem in arriving at a desired output voltage. The R-2R network consists of resistor with only two values, minus R and 2 into R. If each input is supplied either 0 volts or a reference voltage, the output voltage will be an analog equivalent of the binary value of 3 bits. Vs2 correspond to the most significant bit MSB, while Vs0 correspond to the least significant bit LSB. The R by 2R DAC, an alternative to the binary weighted input DAC, is so-called R by 2R DAC, which uses favor unique resistor values. A disadvantage of the former DAC design was its requirement of several different prices input resistor values. One unique value per binary input manufacture may be simplified if there are several different resistor values to purchase, stock, and sort prior to assembly. Now we are going to display about the most significant bit binary input LSB. In a most significant bit there is 2 to the power of 0 resistor, and in binary input there is 2 to the power of 1 resistor, and in the least significant bit there is 2 to the power of 2 resistor. Unfortunately, this approach merely substitutes one type of complexity for another, volume of component over diversity of component value. There is, however, a more significant efficient design methodology. By constructing a different kind of resistor network on the input of our summing circuit, we can achieve the same kind of binary weighting with only two kind of resistor values, and with only a modest increase in resistor count. This ladder network looks like this. Now we are going to discuss this ladder mathematically. Mathematically analyzing this ladder network is a bit more complex than for the previous circuit, where each input resistor provided an easily calculated gain for that bit. For those who are interested in pursuing the intricacies of the circuit further, you may option to use Thevenin's theorem for each binary input. Remember to the considering effects of virtual ground, and now use a simulation program like SPICE to determine circuit response. Either way, you should obtain the following table of figures, where the binary value of 0, 0, 0, the output voltage is 0 volts. If the binary value of is 0, 0, 1, then the output voltage is minus 1.25. As we increases the binary values, the voltage is increases. As was the case with the binary weighted DAC design, we can modify the value of feedback resistor to obtain any span desired. For example, we are using plus 5 volts for a high voltage level and 0 volt volts for low voltage level. We can obtain an analog output directly corresponding to the binary input. 011 equals to -3 volt, 101 equals to -5 volt, and 11 equals to -7 volt, etc. by using a feedback resistor with a value of 1.6R instead of 2R.